Here are solutions to homework set number 7 for ECE 111. In this homework set, we look at using Matlab to integrate different functions. Now, the first problem isn't really a Matlab problem. It's more just sketching integration. Integration is the area under the curve. So think about it like this. If this is my bank account, I start with $2 in my account. That's my initial value. If this is how much money I'm withdrawing or depositing, what's my balance? Well, the balance is the old balance plus the area under the curve, how much I added. So between, say, 0 and 1, I do nothing. If I do nothing, I start with $2, I still have $2. Between 1 and 3, I subtract, so the area of the triangle is 1/2 base times height. So this has an area of minus 3. I come down 3. 1, 2, 3. So wind up right here. Between 3 and 4, I subtract another 3. So come down another 3. 1, 2, 3. I'm now right here. This has an area of about, that base times height, about minus 1.5. So come down 1.5. Now I start adding. Here the area is plus 2, about. So come up 2. 1, 2. I add 4. Go up 4. 1, 2, 3, 4. I go up about 1. Right about here. And now come down 1. Come down minus 1.5. And then stay constant. So the blue line is the area under the curve at any given point. The area to the left is the integral at that point. Problem number 2 is using Matlab for numerical integration. So here's a function, e to the minus x squared sine of x. I can plot that in Matlab. It kind of looks like this. What is the integral of that? Well, when you take calculus 2, you'll be able to calculate that by hand, come up with the equation for the integral. With Matlab, I don't really need to know how to do that. I can solve numerically, though. What I'll do in Matlab is pass x and y. Then what I'll do at each point, take the previous area and add to it the new area. So this is using trapezoid rule. I have a curve like this. I'll take the current output, I, take the previous output, I minus 1, add up the area of that rectangle. The area of a rectangle is 1/2 of the sum of the two heights times the width. Repeat for all the data. That's numerical integration. If I do that, let's take x going from minus 10 to plus 10, steps 0.001, somewhat arbitrary. Here's y. Throw that in Matlab. If here's x, here's y. What is the integral? So what that did is that spun through the data, added up the area to the left, and now plot it. So this is y. This is y. This is the integral of y, the red line. Nice thing about Matlab is knowing nothing about integration, I can integrate functions. When you take calculus 2, I'll come up with an equation for that curve. But for now, we can just say whatever that answer is, this is what it looks like. Give it a different function, sine of 2x plus 0.1 cosine of 12x. When I integrate, here's the function. This is y. The red line is the integral of y. Notice that when I integrate, the high-frequency terms get smaller. The integral looks cleaner than the original term. That's one of the reasons we actually prefer integration over differentiation. Integration reduces noise. Differentiation amplifies noise. Problem 4 looks at animation. Matlab is not designed for animation, but actually does a really good job at it. So this says, let's simulate a bouncing ball. I've got the acceleration due to gravity. So here's a ball. The acceleration due to gravity is 3.72 meters per second squared. That'd be the acceleration on Mars. What happens if we give it some initial conditions, some initial velocity? What path is it going to take? Well, what I'll do is I know the acceleration. Integrate once, I get velocity. Integrate again, I get position. Plot the position over and over again. And that's the dynamics of the bouncing ball. This is if I hit the ground, I just reflect. The velocity was going down, now it's going up. I'll keep on doing that till I get the second bounce. And what that looks like is, let's go over here. Let's close that down. Here's the bouncing ball. I'll start out it goes up, and the acceleration pulls it down. There's the first bounce, comes up. There's the second bounce. When I do that, I hit at 9.3. And here's what it looks like. Here, I turn hold on, so you can sit there and see the path as it goes. But there's where it hits. If I wanted to say, well, I actually want to hit at 10, I could do trial and error, or a little bit of calculation, I can figure it out. This is actually linear in velocity. If I double the velocity in the x direction, I'll double this point. If I want to hit at 10, I take the initial velocity in the x direction, that was 2, scale it by where I want it to go. If I do that, 2 times 10 over 9.3. So here's 2 times 10 over 9.3. Try that again. Launch the tennis ball. Here's the first bounce. And here's the second bounce. Bang! Right on 10. So if you're willing to do some calculations, I can get there dead on. Another animation, and also this is function equals 0. Here's a little shoot game. What this one does is you animate or simulate launching a tennis ball. This is one of the programs on Bison Academy. What you do is you specify the speed, angle of a tennis ball. It then calculates the velocity in the x direction and the y direction. Here's gravity is 9.8 meters per second squared going down. Integrate once, I get velocity. Integrate twice, I get position. Plot the position. Stop when the y part is negative. So if I try that, again, I cannot run this program. This is a subroutine. If I try running it, I'll get an error message. Somewhere, error message, can't do that. But what I can do is I can call it. Let's just say the target is some spot, 95.66. Let's try 60 meters per second at about 40 meters per second at 60 degrees. There's my target. If I launch the tennis ball, like so, it will do some animation and show me what's happening. Return. So there I launched the tennis ball. This was a pretty good guess. The target is 8 meters short of where I am. Hit the target. Well, one way to do that is guess, guess again, guess again. So 40 was too long. Let's try 30. Launch a tennis ball. That was too short. Okay, so let's try 35. One way to get there is guess, guess again, guess again. That does work. That's problem 6. If I keep on guessing, eventually I'll figure out what the answer should be. Try 38. There are better methods than guessing. There's Newton's method. There's California method. Yeah, not too bad. What the California method does is if I have 2 guesses, I'll draw a straight line between them, find the zero crossing, that's my next guess. So the California method, I take 2 guesses. My next guess is find the zero crossing. This is interpolation. I know the first point, the second point. Where's the zero crossing? That's the equation. Keep going, and pretty quickly I'll drive the error to 0. I can also put this in a loop. So this would be a California method. I am going to take my first guess. 0 gives you 0. First guess is 30. I'll then iterate, given those 2, what should the next guess be? So if I try that, here's my target at 82. This is the guess at 30. I missed. Next guess was 35, missed by 7. Then I tried 32.7, off by 3. 33.6, off by 0.02. 0.001. If you're willing to do some calculations, I can get there a whole lot faster. That's function equals 0, something we looked at before. Function equals 0 is a very common problem. You see that over and over again. If I try that again with a different random spot, here the target is at, it's like 52. Using California method or Newton's method, I can zoom in pretty quick. That's homework set number 7 for ECE 111, integration with Matlab.